Hello, welcome to CS825. My name is Jules Hedges. I am your lecturer. So this first video is just going to be a little introductory video to this course. So I'll just say a little bit about what this course is going to look like, what the format's going to be like. Each week, so we have a 10-week teaching term. Each week, I'm going to put out 5 videos of about 10-ish minutes each, which should hopefully add up to 50 minutes, which is what the length of one ordinary in-person lecture would have been. Every week, we're going to have what I'm calling labs, which is at midday local time on Wednesdays. And in this week, which is week 1, we are having a lab, which is going to be pretty chill. Just going to check that everybody has successfully installed a piece of software called Gambit, which we're going to be using a little bit. That's going to be with Ryu, who is our teaching assistant, and also me. And I'm going to see how that goes with 2 of us. It might turn out to be overkill, so perhaps at some point during the term, I will stop coming to those, depending on how it seems to go. The course is going to be something like 2/3 what I'd call classical game theory, the part of game theory that many people learn in many different fields, and then about 1/3 applications in AI. And specifically, I want to focus on applications in reinforcement learning, because it turns out there are some quite deep and interesting links between game theory and reinforcement learning. There are also lots of links between game theory and good old-fashioned AI, that is, say, kind of non-machine learning approaches, so things like multi-agent systems. But I've decided not to focus so much on those, although I'll touch on some topics. So a more accurate title would be something like game theory and multi-agent reinforcement learning. Sadly, I wasn't allowed to change the title from the original proposal. Let me say something a little bit about what game theory is, so what you can come to expect. So traditionally, it's the mathematical study of rational agents who are interacting strategically. And the things I put in red here, I'm saying something about on the next slide. So what I mean by mathematically is that this is going to be mostly a kind of conceptual theory course. There's not going to be too much programming in this, although there'll be some. Then rational agents. Well, an agent is, you have some intuitive idea of what an agent is. It's an autonomous thing. It can interact with other agents. It can interact with an external environment. In a game, an agent is like a player who can like make moves, observe the game state, that kind of thing. Now, a rational agent, this is a kind of standard useful assumption that is quite ubiquitous in game theory, which is that all of our agents are perfect, that they kind of act perfectly according to their self-interest. You don't consider things like computation time and computational resources, that kind of thing. And of course, for us in computer science, that's of limited usefulness. So what we would like is to go from rational agents to intelligent agents. So I consider intelligent to be a weaker and more realistic property of agents than rationality, because rationality says that your agent's perfect. Intelligent agents are, well, it's sort of, in AI, it's our business to figure out what it actually means to be intelligent, but this means it's equipped with some kind of computational or cognitive process that models how it plays a game, or how it interacts in a situation. And the last word here I've highlighted is strategically, and this is kind of important. So what strategic means as a technical term is that in game theory, actions are usually kind of pre-planned. So the plan for how you're going to act is called a strategy. And the optimality conditions are going to be applicable to strategies, not to actions. So we're going to say that We don't have good moves, we have good strategies in game theory. Okay, this is just a kind of taste of the things that are coming. Game theory has lots of applications, not just in AI and machine learning. So of course, its most famous application is in microeconomic theory. Several of the pioneers of game theory won economics Nobel Prizes. It's also applied quite famously in military strategy, especially in Cold War nuclear strategy. It has very important applications in ecology, in the study of like food chains, food webs, this kind of thing, ecological networks. And there are other applications in computer science. There are applications in computer security. There are some slightly unexpected applications in program semantics on the theory side. And then these are the two that are of interest to us. So some in what I call good old-fashioned AI, and then some in machine learning, which is what I want to focus on. Okay, the approximate outline of the topics we're going to cover is this week and next week, we're going to be looking at what's called normal form games. Then in week 3 and 4, we're going to be looking at what's called extensive form games. So roughly normal form games are like games where everything happens simultaneously. Extensive form games have a notion of time or a state that changes over time. Week 5, we'll be looking at Bayesian games. Week 6, probably repeated games. Week 7, Markov games. So these are kind of particular special cases of games that are used for certain situations. And then the last 3 weeks, we'll be looking at reinforcement learning. So this is not a sharp jump from one topic to another topic, because these things blend continuously into each other. So by the time we're studying Markov games, this is starting to look recognizably like reinforcement learning, or rather the other way around, reinforcement learning looks recognizably like Markov games. Okay, a little bit of administrative stuff. So hopefully all of you by now have found the Mattermost channel. So please don't hesitate to use the channel as much as you can. Online is difficult, so it'd be nice to actually talk, just chat on there. You can also email me. I assume you can find my email. I suppose I'll put it on the My Place page. But it would be nice if anything that resembles a kind of technical question about the course content is asked in public, so everybody can benefit from the answer. Okay, we're going to have weekly exercises, which will be self-marked. So in the exercises that you'll be done, that I will put up in week N on the week N topics, in week N+1 on Wednesday, we'll have the call, and then we'll go over the solution. So I expect you to do the exercises that I put up at the beginning of week N by the middle of week N+1. Okay, for assessment, I'm actually recording this video last because I had a last minute change of heart about how I wanted to assess you. So in the end, I've decided to go with 30% take-home exam, or at least what I'm calling a take-home exam. The university considers it formally a type of coursework, which I will tell you more information about later. This will come somewhere towards the end of the term, and then individual mini projects. So I'll also tell you more about this later in the term. Okay, that's hopefully all the administrative stuff out of the way. Oh yes, the course materials are as much as possible on GitHub pages. That's for 2 reasons. One is I kind of hate My Place. It's kind of a pain to use from the administrative side. And the other is I like to make the course materials public. Just inherently, it's a good idea to make things public. A couple of links which are kind of private to Strathclyde, where you need to be logged in, will be on My Place. So I will use My Place for a few things, but kind of course materials, the the content of the course is going to be on GitHub pages. Okay, so hopefully that's now all of the introductory stuff out of the way. So see you in the next video where we will start on the first topic.